Okay, in section 1.3, just some mathematical models. Uh, You are familiar with some of these, maybe most of them, perhaps all of them, from physics. So there's nothing new under the sun. What we want to do is to be able to see how important is the derivative or the differential equation, how important is that with certain models, certain physical models. I will hasten to say that it is the differential equation that is observed initially. And then from there, you can build algebraic, kinesthetic equations that you normally would probably see in physics. So the origination of a thing, we believe, typically occurs with some type of rate of change, some type of shift in the movement or the velocity. Any kind of shift, any kind of change really speaks of a derivative. And from there, if you're able to build an equation, we can talk about a differential equation. So the first model, falling bodies, we use Newton's second law, where force is equal to the mass times acceleration due to gravity. That acceleration is a second derivative based on the position. And so we can either talk about the second derivative in terms of s, the so-called displacement, and sometimes we could talk about dx over dt, x as being the displacement. Either way is still said to be tantamount. Or you can talk about that second derivative as being the derivative of the velocity. So you can talk about the mass times dv over dt, which gives us the same thing. If there's a falling object and you consider the resistance from air, then that resistance could be in various forms. Just a standard resistance is said to be the velocity itself with respect to gravity. So the slowing up of the object could be minus k being just a constant of proportionality that's to be determined times the velocity. Sometimes it may slow up even quicker, so it could be a velocity square. And then there's several other types of resistance that could occur as well. So the differential equation that we have in that regard, looking at the so-called force equation, is that here the force is the mass times the acceleration due to gravity, or the change of the velocity. So which is here the mass times the acceleration due to gravity, which is g, if it's metric, is 9.8 meters per second square, or it could be in the English metric, the English system, the English units. So either one is fine. Minus if there is air resistance. If there is no air resistance, then we use this, right, which is the same as that, just without the mass. And just various ways of how you can write those equations, whether we use v as velocity or whether we use s as the so-called displacement. A second connection to the force would be the force that's exhibited by the vibration of a string. And so there we use Hooke's law. And that becomes a combination of Hooke's law and Newton's second law. So somehow we can tie them both together. So here we have the force is the mass times the acceleration due to gravity. And then in Hooke's law it says that the force on a spring is said to be directly proportional to the distance of the stretch. And so Hooke actually calculated the stretch as being s, and you see this little movement here, and they have s. Well, s is basically in the confines of x, if you will. And so we have, for Hooke's law, F is equal to x times k. This spring is trying to normalize itself. It's trying to go back to its rest or its equilibrium state. So it's going to be a negative on that particular force. So for Hooke's law, F is equal to some negative k times x to try to restore you back to where you started from initially. From these two equations, what two equations? Well, this side right here is Newton's second law, that F is equal to the mass times the acceleration. Right? And then this guy right here is Hooke's law, that the force is equal to some negative k, restoring force, times x. So we put them both together. And what that gives us is really the groundwork for harmonic motion, or the motion that is due to some type of movement, whether it's a string or is really applied to almost any force nowadays, the force that's exhibited from some mass in space. And so we can determine later on in this course an equation for motion from the setup for numbers 1 and 2 for these models. The third model, talk about series circuitry. Here the concept will be based on Cherkov's second law, and in that particular law, he dealt with, let me see if I can pull up an image. If you want to consider the circuit, the current on a circuit, if you have some kind of loop here. So here, Cherkov's second law states that the impressed voltage that is said to be on a closed circuit must be equal to the sum of the voltage drops of the entire loop. Basically, the energy here is the electricity that's going into the circuit must be the same amount that's coming out. So whatever's going in has to be conserved, and so the energy that goes in must be the same coming out. Now, sometimes you have resistance, so it kind of slows up the current, but calculating the energy on the current must also equal up to the total that goes in versus what comes out. So if you have a voltage drop here of this particular circuitry, here we have inductance, some kind of capacitor that somewhat tries to store up, a certain amount of energy. The resistance is trying to retard it, trying to slow it down, so that you have certain items on the board that you don't maybe want to overheat. You want those items to receive certain charges at certain times or a certain amount. So we have resistance. From here, we're able to create a differential equation. That's where I come in, right? So the differential equation here for this circuitry, we have 4 items, right? We have this voltage drop, we have inductance, and inductance is given by this expression, this L times the second derivative of the charge. Q is the so-called charge. And then the resistance here is given by R times, this is really I. I is equal to, I is the so-called current, is equal to the rate of change of the charge. So it's the inductance plus some resistance, R times I, plus here the capacitance is given by 1 over the capacitor times the so-called charge. That's equal to the the electric voltage that's being dropped on the so-called circuit. When you start adding things to this, then obviously you start adding components even to the differential equation as well. Let me see if I can give you a simple one. Let me back up. We have series circuit. We have the inductor or the inductance. So it's this inductance L that's given in henries times some kind of, you see how I there is the current, and so here and Q is the charge, and so the inductance is given by this L times the change of the current, the resistor R times I or I times R, and then the capacitor. What if you have a circuit that only has the resistance and inductance on it? So the question, how would the differential equation look with a voltage drop on an inductance and resistor? So we have this voltage given by E of t, resistance by I times R, and inductance is L times this di over dt. So this would imply then that we have L times di over dt plus R times I. Here, this so-called current is a function of time, right? So R of t, if you will, and this is equal to E of t. This is a differential equation. What is the order of this differential equation? It's the first order. And is it linear or is it nonlinear? I heard both, I think. I think I heard both answers. I think I heard somebody said linear. I think I heard somebody say no. Bless you, bless you. It's linear. It's linear in what? That's the question. What is what would be the dependent variable, and what would the independent variable be? So time is the independent, right? It's dependent on time, right? It's a function of time. The so-called voltage E is a function of time, right? It's E of t, right? So what would, in this particular equation, what's the dependent variable? Yes, sir. To the current, which is I. Right? So you have I, then you have the derivative of I, right? di over dt. I is raised to the first power. di over dt is also raised to the first power. So, and their coefficients are also restricted, by time as well. So L is a constant. It's just a number, right? The resistor is just going to be a number as well. Um, so yes, it's a first order linear differential equation. We will solve those types of differential equations in this class. Okay, very good. We could talk about a differential equation of how to determine the amount of time it takes to cool an object. An object, if it's some kind of solid, if it's in the freezer, if it's taken out, if it's in the furnace, and if it's taken out, can you give us some kind of differential equation that can compute the time it takes for an object to cool down? There we use Newton's law of cooling. Newton's law of cooling, which is a direct proportional particular problem, which says that the rate at which a body changes temperature, that rate is classified as d capital T, right? The rate of change of the temperature with respect to time. So d capital T over dt is said to be directly proportional. So when you talk about direct proportions, there has to be some kind of constant of proportionality. It's directly proportional to the temperature of the body, basically the difference of the temperature of the body, which is the object, capital T, minus the temperature of the surrounding medium, T sub m. And we want to be able to solve a differential equation of that form. Talk about population growth and decay. You've seen this guy even back in algebra class. You probably wasn't given the differential equation, right? But you should have been given that back then, Would have made life a whole lot better. Right? So they didn't tell us what was really going on. It's almost like with your parents, and when you're young and you say, I'm hungry, and they just feed you. Or you need some clothes, they just give you some clothes. Or you want a toy, and they give you a toy, You want an Xbox, they just, somehow Xbox just appears, right? You ask your mom or your daddy, and you say, I want a bicycle. And, man, and as a kid, you didn't work for anything. It just showed up. Well, that's how algebra was, Algebra stuff just showed up, man. You don't ask any questions yourself. It just fell out the sky, and I just started playing with it. No, somebody had to sweat and labor over, how you got that bicycle. Man, mom and daddy had to work for it. So algebra was like stuff just like a child, just fell out of nowhere. You don't know how. But then you become a man and a woman, and you get married, and you have children, and then your kids start asking you for stuff, and you're saying, man, this stuff costs. Right? You got to do some work, I got to, and you're telling your kids, hey, I can't, not right now. You think money grows on trees, right? So as a parent, you have to go and you do some work. With differential equation, it's like a parent, right? We're going to show you, how you got the toy, okay? Which is a whole lot better. And then you say, hey, I'm going to teach you something to your son, to your daughter. And teach you how to respect what you're getting. Or you want to try to give them some DE even when they're taking algebra. That's good. That's good stuff. That's good stuff. So we can talk about population growth or decay. We still use the fundamental equation here that the rate of change of the population is said to be directly proportional to the population at the current time. Population here depends on T, depends on time. So we have population growth here for positive coefficient. We have population decay if it's negative. There are other equations that takes this guy and expound on it, but I want to consider the fundamental one, and then how to solve these guys using differential equation. Okay. So the rate of decomposition or decay, see the negative there? The negative. So it's really the same problem as this guy right here. Letters are not humans, right? So it's dp over dt. This is dy over dt. So the y is the same thing as the p up there. Right? So letters are not human. So you're going to always change the letters, and there's no argument. Now, when those letters and variables start arguing back with you, it's time to change your major, right? Something like history. I loved history. It's one of my favorite subjects. I want to study that, man. All my history teachers, those guys, they were like, I don't know, man. They were like prophets or something. They would just talk this stuff like they were there. I had this one guy down at Wallace and Selma, and he was a retired colonel in the military, and he would talk about, all these escapades, from if it was Napoleon or if it was Hannibal, whatever, Charlemagne. He would talk to you as if he was right there in the squadron, with the other guys. I used to love it. Let me tell you here's what Hannibal said. Now, he talked like he actually heard Hannibal himself. And every day he'd just come in class, he'd just sit right here on the desk and he just talked, man. For 1 hour he just talked, like he was right there. That's what I'm talking about. That's how you do it, man. But anyway, we studied mathematics. Okay, let me move on. I'm talking too much. I want to work a problem before you go home. So I want to give 3 problems. One deals with population growth. One deals with population decay. Then the other is concerning Newton's law of cooling. Let's look at these problems here. So the first one, suppose an experimental population of fruit flies increases according to the law of population growth. So when it says that, I want to be able to write a differential equation. Differential equations that we have are the ones that I've given already up above. So here it says that the rate of change of the population says is increasing. So this is some constant k. It's going to be positive. It says this guy is according to the law of population growth. So dp over dt is equal to k times p. I want to solve this differential equation by separation of variables. I think there was a section in calculus, maybe it was section 6.2, where we dealt with population decay, population growth, and it was an introduction, if you recall, to differential equations. And in there, we solved by separation of variables. So I'll show you. Solve the DE by separation of variables. It's like the easiest form of differential equations to solve, like the easiest one. So the name of the process, it says it all. I'm going to separate the variables. I want to get the variables together. Now, you don't do any, unmathematical things to get them separated. Like, can I just put this over here? No, you can't put that over there. You get to do some math, right? I thought I could just. No, you use math. You don't know all the stuff I've seen. You can't do that. No, man, you're making me cry. But anyway, we're going to use some math, right? I'm going to get the P, the DPs together, and then we get everything else somewhere else. So here, we count the derivative as a as a ratio of differentials. So it's actually dp divided by dt. So I'm going to multiply both sides by dt, divide both sides by p. So we said this implies that 1 over p times dp is equal to k times dt. The variables are separated. So the variables are collected in terms of like terms. So from here, I'm going to integrate both sides. We make use of the fundamental theorem of calculus, where in terms of if you have derivatives and you want to solve for their base form, we use the idea of an antiderivative, right? So this implies that we integrate, we have the integral of 1 over p dp is equal to the integral of k times dt. Well, this implies that we have the natural log of the absolute value of p is equal to k times t plus a constant, let's call it c sub 1. Since we're solving for population, that really means I want to get the p by itself. That's the natural log of p. So how do I get the p by itself? It's the natural log. We exponentiate. Here we have to exponentiate everything, both sides, right? So mathematics is just the principle of opposites, which life itself is based on the same concept. So we have e to the natural log of the absolute value of p is equal to e to the kt plus c sub 1. All that stuff is up there in the power bracket. Let me go this way. So the left side is p, assuming that the population is going to be positive. We don't want a negative population. It means everybody is dead, right? So this is equal to e to the kt times e to the c sub 1. Let capital C equal to e to the c sub 1. And so this is what you've seen in your algebra class, that the population is equal to c times e to the kt. You've seen that before, right? So that was algebra. That's just the thing that just fell out the sky. So, oh, man, thank you, Mama. Thank you, Daddy. Right? But where did that come from? Well, now you're the mama. You're the daddy. You got to go get it. You got to go get that dollar. You know, man, you got to work, you know. And it's a blessing because you go home and you bless your kids and they just think you're just the super mama and the super daddy, You know, my kids, they see us, they say, oh, thank you, you're the best daddy. I'm like, you don't know the half of it, son. Hey, wait till you become a daddy and you're going to see what it's all about. Amen, amen. Okay, so that's a T there, and excuse my French. It's a T. Now we can solve the problem. Now we can solve the problem. So from here on out, anytime you're given a population problem, once you've solved it, the DE, then you would just use that formula, right? It says there are 100 flies after the second day of the experiment and 300 flies after the fourth day. We're not given what happens on the first day. Typically with, these types of problems, they're going to tell you, here's what happened, the very first thing. And the very first thing assumes that the count t equal to 0. Here they don't give us that. They give us this. Let's go back up. They give us that when p is equal to 100, t is equal to 2. Right? And when p is equal to 300, t is equal to the fourth day. Let's take that information and see if we can produce terms like the constant c and then this constant proportionality k. So I take 100, that's equal to c to the e to the k times t, so that's going to be 2 times k. Now from there I can isolate the c and say that c is equal to 100 times e to the negative 2k. Now come on the other side, over here I have 300 is equal to c times e to the 4 times k. I'm going to replace that c there, replace this c with this information right here. Trying to eliminate some of these variables. So here I have 300 is equal to 100 times e to the negative 2k times e to the 4k. At least from there I can isolate k. Right. So taking that, I have 300 divided by 100 is equal to e to the, multiplying two bases. Here we're going to just add the exponents, right? So this is e to the 2k. Well, that implies that's just 3 is equal to e to the 2k. Here I have an exponential form. Its opposite, its inverse, is the natural logs. We take the natural log of both sides. So this implies that the natural log of 3 is equal to the natural log of e to the 2k. That just gives you 2k. So here, 2k is equal to the natural log of 3. That is, just k is equal to the natural log of 3 all over 2. So that's k. Right, so we have p is equal to, we got that c times e to the kt. This is going to be t times the natural log of 3 all over 2. But c is equal to that 100 times e to the negative 2k. So we're going to plug that in. So p is equal to 100 times e to the negative 2k, and that's times this e to the t times the natural log. Let me fix that up. Since I got a k there, this is e to the kt. So this is 100 times e to the, I have the same base, so this is k times, this is k times t minus 2. Okay. So p is equal to 100 times, we know what k is, right? So k is this natural log of 3 over 2. This pen writes so thick. The natural log of 3 over 2. And then this guy is times t minus 2. Let's go back and look at the question now. The question says approximately how many flies were in the original population. That means find capital P when t is equal to 0. Find P when t is equal to 0. So this is P is equal to 100 times e to the, if t is 0, then I have this natural log of 3 over 2, really times negative 2. So the 2's cancel out. I have 100 times e to the negative natural log of 3. Just going to simplify that. This is 100 times e to the natural log of 1 over 3. And e to the natural log of something is equal to that something. So this is 100 times 1 over 3. So P is equal to 33.3 flies, or just 33 flies. Okay. Any questions there? I got time for one more problem. Just got the next one here. This is the rate of decomposition of a substance is proportional to the amount y at time t, so that dy over dt is equal to negative k times y. If you will, this guy simply implies that y is equal to c times e to the negative kt. It's the same problem from before, but since we know that it's decaying with that negative, it's the same equation type. Instead of saying exponent is k times t, it's negative k times t. Okay? And if you don't see that, you can go back and solve it, the way we did with solving the DE, and you'll get that when you finish. Is everybody okay with that? Okay. So here we have y is equal to c times e to the negative kt. So let's look at the problem. It says find k, so find the constant, if y changes from 1,000 grams to 500 grams in a half an hour. So here we have y is equal to 1,000 grams when t is equal to 0. And then we have y is equal to 500 grams when t is 1/2 hour. All right. So we stop there and see if we can try to solve for these constants. So we have 1,000 is equal to c times e to the negative k times 0. Well, that implies that c is equal to 1,000. E to the 0 is just 1, so we just have left c. Just have left 1,000 is equal to c. And so then for the next one, we can go ahead and write the equation with the value of c. So y is equal to 1,000 times e to the negative kt. Plug in y to equal to 500. That's equal to 1,000 times e to the negative k times 1/2. So this implies that 500 divided by 1,000 is 1/2. That's equal to e to the negative k, well, just negative k over 2. Let's say that. We can solve for k, just exponentiate both sides. So here we have the natural log of 1/2, excuse me. is equal to negative k over 2. So that implies that k is equal to negative 2 times the natural log of 1/2 and that value for k if you think about it, this is 2 times the natural log of 2, and that's the natural log of 2 to the second, so that's the natural log of 4 for k. And I believe that, I think that's, that was the question, I believe. What's the, find k. So the problem is really y is equal to, c was 1,000 times e to the negative k times t. So we just say negative t times the natural log of 4. And if you want, you can fix that up if you wanted to. You can get rid of the e and the natural log. You don't have to, because the question was just find k. Well, I saved one there for you. That last one there that deals with Newton's law of cooling. I'll leave that one for you. And then the homework that's online in WebAssign. Okay? Any questions? Thank you.